Hi, this demonstration problem will be one in which we build something called a diagram or a Venn diagram or a set perspective for a probability space. And it'll help us then catalog one way of looking at a population and breaking it down into its shared components. So I'm going to start with a description of such a problem, one that you will see in your lab, I believe, your lab 5, and it's about a population of phone users, of phone service users, consists of 35% cell phone use only, 20% of cell phone users that have landlines, 15% of landline only users who are listed in the phone directories, and 10% of landline only users who are not listed. In the phone directories. Okay. Change this to make it a little bigger, 45%. And now I'm going to draw the probability space before I look at any questions about this particular type of question. So first I'm going to imagine a square where the square is all users, all in the population. Now, if I look at everybody in the population, that would make 100% of people, right? So the orange square represents 100% of people. Now, of all those people, 45% of them so that's almost half. So I'm first going to shade this in half and then back up a little bit. And I'm going to then say 45% are cell phone users only. So that's the green part. 20% use cell phones and have landlines. So what I'm going to do now is paint a different color of people who have cell phones, but also have landlines. And that's 20% of the whole thing. So if I were to draw halfway there, and then halfway there, that's a quarter. So I'm going to cut shy of a quarter, that's 20%. So notice how I'm still talking about everybody. So I'm keeping my colors within the borders of the box, and I'm trying to identify where these boxes are. And I'm noticing, fortunately, that these boxes do not intersect with each other, do not overlap with each other. And that's an advantage because it'll help me simplify not having to worry about where these colors overlap, because they apparently won't. Then 10% of people have landlines, only landlines, so they don't intersect with either the purple people or the green people. And they are not listed in the phone book. So I'm going to put these people, and I'm going to put them in a blue color. And this blue color is going to be half of the purple color. So that 10% are these people. And then the orange people are going to be the fourth category here. And the reason why that orange doesn't overlap with the purple or the blue or the green is because they're landline only people. So they don't have cell phones. So they don't have anything in common with the green or purple people. And they are listed in the phone book, which the blue people are not. And so the orange people are going to be in size, just the same size as the, and then some. So they're going to have like 5% more. You know. And so if you look at the data, then the orange people are 0.15, the green are 0.45, the blue is 10%, and the purple is 20%. Now that doesn't add up to 100%, that only adds up to 90%. And so what is 10%? 10% are the white spaces. So the stuff that I'm going to cover in X's here are people who don't have cell phones or landlines. They just don't want to be communicated with via these two device types. So all these people out in the borders here are people who have neither cell phones nor so that's what X represents. Oops, missed some of the X's here. Okay. So now that I have the probability space in this format, I can ask questions such as, what is the probability that people have cell phones? What's the probability that you pick a person from the population and they own a cell phone? And in this case, we're going to be applying the addition rule because people may have cell phones because they only have cell phones. Or, alternatively, they could have cell phones and landlines. And so the answer is just 0.65. The other 40% of the other 35% of people don't have cell phones, so they don't count. Okay, so that's a way to use the addition rule from a Venn diagram to collect information about this. I could also do the math with respect to the following computation. What is the probability that someone has a cell phone conditional on that they have a landline? So given that you see they have a landline, what's the chance they have a cell phone? And that would be, given that they have a landline, means there's 45% of people who have landlines. Where are the 45% of people who have landlines? The 45% of people who have landlines are the purples, the orange, and the blue. Okay. So purple, orange, and blue is where this 45% is coming from the condition. So notice how this is a condition, landline, and that this 45% refers to this 20, this 15, and this 10. Now, what's the chance that they have a cell phone? Well, in those groupings, the only people who have cell phones are the 20% in the purple group. Because those are the only people who have cell phones. The 45% don't count at all here, but in green, because that green 45% is nonsense. It is not people who have landlines, so they don't count in the conditioning space. The overall space is now just the people who have landlines. And so they're only either purple, orange, or blue, 45%. So when I divide 20 by 45, I get 4 out of 9. So that's 0.4444. 4 ninths. Okay. So that would be the way to answer that. What do we know by looking at these two calculations of probability? The calculation of probability that we call the marginal rule and the conditional rule. We see that the answers are not the same. One answer is 44%, the other one is 65%. So therefore, what can we say about cell phones and landlines? We can say that there is a dependence. Cell phone and landline use are called dependent events. Having a landline means you are less likely to have a cell phone, would be another way of saying that. Having a landline, people who have landlines are less likely to have cell phones because they're only 44% chance likely to have a cell phone, not 65%. Okay, so there you have a third type of probability space, one that we call a set or a Venn diagram type of probability space. I hope that this, along with the prior two video examples, one of a tree diagram and the other one of a table, are all helpful in helping you understand the 9 rules of probability that explain how it is that we arrive at metrics of uncertainty and how likely it is to see things happen, and that enriches our ability to make decisions under uncertainty as well. Thanks for watching this, along with the other videos as well.